Our next speaker is Armen Vagharshakhyan, who will speak on lower bounds for L1 discrepancy.
Hi, I wanted to give the talk about this topic called discrepancy. The talk will be on a very, would sound very primitive and straightforward, and that's exactly, if you get that impression, that's exactly the impression I want you to get, because if something hits the best constant, then something's gonna be very, very clear, and things would come to each other very naturally, so it would end up on somewhat a high school level. A second reason I want to give a very primitive talk is that somehow seems like in this theory we are stuck with the methods that we are using. And if we are looking for some new idea from new people, then I ought to give very detailed and clear and simple things so that maybe some people from other areas will come up with ideas. So let me be very simple. I take n points on unit interval, and I have a function on 0, 1. I want to approximate its integral by the average of its values that it takes on that n point set. I assume that that function is in the class of bounded variation. I do integration by parts. I do Abel summation, and I group things. That's it. And then, in this class of functions of bounded variation, of course, I can split it into two terms. One depends on the function only, that's the variation, and the second depends on this positioning of points only, and that's a certain quantity that describes how, in a certain sense, uniform this sequence is in 0, 1. Now, this is all clear in one dimension, and good choice would be just partition the interval 0, 1 in n equal parts. That's it. I mean, there's nothing like better you could do. But what if you think about the very same problem in 2, 3, or higher dimensions? Then interesting things become. So again, I'm thinking about quantities like that erase when you're doing numerical integration in the class of functions of bounded variation. Of course, if we think about a different class of functions, there's a different notion and a whole different technique. So the class of functions is, of course, important. Let's think about 2 dimensions. So what I would have here is a unit square, a finite set with n elements, and the following quantity. I take a rectangle like that. I calculate the number of points that this set has in that rectangle. And I take out the, the expected number of points. Would this be a uniform distribution? I want to understand how large this must be. And I want to come up with sets for whom this function as a function of xy is small in some sense, in sense of L infinity norm, L1 norm, or something. It turns out already starting from here, or even more, of the same problem in higher dimensions, problems arise, and a lot of open problems are around, even though something in one dimension is true. So I was thinking about this quantity and its L1 norm. So you're fixing the number of points. You're thinking of a good distribution. And you want to understand the asymptotics of this thing as n goes to infinity. That is, sets for whom this is small and how large it has to be no matter what the set is. Now, I have to cite some results on the area. Actually, there are only 3 results on the area that has ever been obtained. One is that this is of the order 1 over square root log n. So this is bounded. This is the result by Davenport, 1956. So bounded by constant. I read plus infinity wrongly, constant. The lower bound is that it's bigger than 0.007 39. This is a result of Gregor Halash of 1981. And the third result is that it's actually bigger than 854. And this is the result I'm going to talk about of 13. So surprisingly, it's just, every 30 years. Nothing else is known literally. Yeah, root log n is the right order. We are thinking about the constant in front of root log n. So this is it. I will show it, of course. It's not something that you could quite see, like, wow. Because, for example, if you think like of a good distribution, like, something like that, a lattice, this is very bad. Because what you would have, if you think about something like that, very small rectangle with small area, you expect very few points, but there are actually many of them. So it has to be somehow, you would say random, but if you take n random uniformly distributed things, on the average, it's not going to be of the order log n. It's going to be of order root n, much larger. So this is a very, specific constructions and something very specific. So this is the sequences obtained by that are used in this quasi-Monte Carlo methods. And instead of just taking random sequences, you take some specific things and get much better estimates. And what I wanted to talk about is that, from the right viewpoint, this is just doable by very primitive methods. Okay? So if you allow me, I would go down and start talking about the proof, because I promised. Okay? This is something phrased in dimension 2. Same things are true in higher dimensions, and nothing more is known in higher dimensions.
What do you mean same thing?
The same bound, and it's not known,
With the same constant?
This thing. The methods just, translate literally to higher dimensions. If you want to, this low bounds. If you want to get, something better, you cannot exploit this fact that it's a dimension for lower estimates. Like, no way. I will show why, and it gets really interesting, and that's the point. So I will talk about this method for this what seems to be a geometric problem, but it has to do with analysis through a method developed by Klaus Roth in 1954. I'll show a bit of modification of that method, but I want to show this relation very clearly so that we see that it's actually an analysis talk. So suppose I have that set, and I have these endpoints. Okay, it happens. I will take a small power of n, like the small n, to be like that. It's matching a 2 to the n to capital N, nothing more. Then I take an I, which will correspond to the geometry of rectangles, to be a number in between 0 and n. And then I will be taking, this is my set P, it's fixed. I will be taking rectangles whose one side length is 2 minus I and the other is 2 to the I minus n. So that the total area of this rectangle is 2 to the minus n. And at least half of these rectangles will not contain any point of my set. So I think of these dyadic rectangles, that complete all the picture. Well, it's 3 there, not really dyadic, but OK. And what I do is the following. Suppose there's no point of that set in that rectangle. OK? Then I draw L infinity normalized Haar function there. So minus, plus, plus, minus. I draw everywhere where there's no point. When there's a point, I look at smaller rectangles with the same geometry relation for sides and do the same thing. So it's a smaller rectangle here with sides 2 minus I minus m plus 1, and same here, so that the relation between sides is the same. But it's now a smaller Haar, here, 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 except the one rectangle when there is a point, and then I continue doing the same thing there. So if I think as I ranges for every fixed I, the functions that I describe here, fi, is a function that takes the values -1 and 1 only. It's a sum of Haars. For every I, there's a certain geometry of these Haars. Different I's, different geometries. So they're orthogonal and independent and things like that. Moreover, one can just count that if you're thinking about this function and this rectangle doesn't contain a point of your set, then there's a certain dot product between this Haar function and that discrepancy function. You can just calculate it. Then on the first level, there are too many good Haars. The ones that are on the first level don't contain any point. So if you calculate this integral, the Haars on the first level will sum up to a constant, and the Haars on smaller level will sum up to something of lower order. So what you get is there are m plus 1 functions. Each of them forms an angle with your function dp. Of course, the actual choice of functions fi depends on the set p. If the way you move it, these fi's, move. But now the question relates to a somewhat a question in analysis. You have functions, you have orthogonality, you have a certain angle. What you want to have is estimate on L1 norm from below. I mean, one stupid estimate will be, of course, if you do like that. dp L1 norm times this function L infinity norm. Cool. But you want to exploit the fact that you have several of these functions. And you want to balance it. You want to do something. Then when it comes to dot product, it's large. When it comes to L infinity norm, it's small. Seems quite natural, right? Now, if we have the right phrasing, then it would get quite easy. Let's do that. I would need a chalk once I find it. Here. What I want is to dot dp with some combination of these functions fi. This fi is having the same role, so I can take some symmetric function, which, because of this, would end up in a function of a sum. So I could just write like that. I write root n. It's good to write it here because we'll go to the normal distribution. So suppose I'm looking for a function t which is, say, analytic. I want to find a function like that, which would have a small L infinity norm. And when it comes to dot product, I want to be able to expand it and calculate everything in a way that these terms, dpfi, that give me a constant, will be many. And the other terms would not disturb me much. That's all I want. I find the best function. I find the best constant which is achievable by this method. That's it. Okay, if we think about it, of course, suppose this is an odd function. Okay, linear term will be dp and then derivative times this. This will have an impact. But remember, we have a very specific construction saying that the function takes only the values -1 and +1. So, for example, linear terms will arise not only from the linear term of t, but also from higher order terms of t. Of course, it's like that. So imagine it's the third order term, f0 plus f1 cubed. We all know what it's equal to. Once this is like that, it is 4f0 plus 4f1. So it's a linear term arising again. So if you have this, this hint of it's exactly like that, you get more and more and more linear terms, and due to that, you can improve the bounds known before. So generally speaking, you can say that this, or the linear term of this, would correspond to something like that. So all the integrals dpfi over i's, this will be of the order small n, times a certain thing, depending on t. And that certain thing, this linear part that you can extract from t, you can just calculate. It's going to be like that. So linear part of t, paying attention to these things, goes just to this operator. Some combinatorics. Well, then all you need is find an odd function whose L infinity norm is 1 and for whom this operator is maximized. It's going to be signed because x e to the x squared half is maximum at 1. So that's all. Take the function sign here. The linear part will give you, this is n, and with root n, it's giving you that. So will be n divided by root n times a constant, and small n is about logarithm. So everything matches together, plus higher order terms, smaller equal than the L1 norm and the L infinity norm of sign. As for the higher order terms, it turns out they are negligent, again, because of this construction, because if you have Hrs with different geometries, their product is a Har on a much smaller, set. And you can calculate that when you dot it with dp, it's of a lower order, so that you are done. So we could see with the right construction and the right viewpoint, you get it all. And you get the best one can get by this method, it turns out. Get the best function, it's quite clear. What you don't get is any hint about, can we do something smarter in higher dimensions? Why things would not work, I will show. If you think about this construction, 2 minus I and 2I minus n. Imagine you are doing it in higher dimensions. What happens in 2 dimensions, if you have 2 rectangles corresponding to different geometries, on each side they are different. Because if you have 2 pairs of numbers whose sum is n, and as pairs are different, then each of the corresponding ones are different. In 3, it's not like that. You could quite have, 3 numbers who add to the same 3 numbers are different as triples. but on some coordinates they are the same. So what you have here is independence and things like that. You might not have all these things in higher dimensions, because two of them might end up not in a product, not in a sum of Haar functions, but sum of things which are Haar in one direction and constant on the other direction. This is exactly the things that you will not be able to estimate here. You'll have to throw it away. But this will be so big that they will affect your estimate. And you can't do anything about it at all because of this phenomena. Of course, if you know per se what this particular example of a set is, for whom this optimal bound root log n is achieved, you can, for that particular set, go ahead and do the calculations and get something. But for the general case, you just can't. So the idea is maybe someone can exploit this fact, but the fact that it gets constant in some dimension and you can't do anything about it and you throw it away bluntly is just killing everything for L1. You can get estimates for L infinity. You can get very well things for L2, not for L1. So that's a problem that we have. Now, these results, actually, you can compare the lower bounds that you get on the L1 norm are very close to the upper bounds that you get on L2 norm. What turns out, if you have a set, there are specific constructions known, for whom the L infinity norm is of optimal order, and the optimal norm order of L infinity norm would be log n. And at the same time, the L2 norm would be of optimal order and a very good one. It would turn out that the L2 norm would be very close to L1 norm in terms of constants. So what you would have for these good sets is, for most places, it's plus or minus its L2 norm, root log n, and at some very few places it peaks at log n, and you can't avoid these peaks. So that's a very interesting phenomenon going out, that the L infinity norm is achieved on a very, very small set, because L1 and L2 norms are close and of order root n. So something very strange is going out on there. Even though you can control this, these guys have to peak. This is, even in 2 dimensions, these have to peak like that. So I think that's pretty much it of what I was going to talk about. Oh, yes. It's C if you want to write. I'm sorry. PP and 1 over root log n is, you write C1 and C2, something like that. Yes. The thing for C1 is actually very interesting. There's no specific construction that is good for C1. What you do is do it through doing C2. So I can write down the constants too, if you're wondering. I never remember them, but so the lower would be now 0.00854, and the upper would be 17905. And these upper bounds, it's a result of Faure, Billy-Schammer, Pirsich, and Schmidt of 2010. The upper bounds, there's a whole history of upper bounds because people come up with neater and neater constructions. I can tell you some of constructions right away. For example, of course, if you take the first coordinate to be uniform and the other will be a fractional part of root 2n, something like that. This would not the best constant, but the best order. Then you can do like a projection of a hypercube that would be closer to best constant and things like that. I can maybe try to draw some things like that there, but they are not optimal. It's just that there's this idea that if you're getting to good thing, then it has to have some structure. The ones when first coordinate is kn and the second is fractional part, say root 3n, are hard to get the good constant. But there are other ideas too. I will show you one. Let's have pictures, right? For example, it's not exactly this, a perturbed version of this, but that's the hardest thing I can draw on the board. Sets like that. It's very interesting. You get the left part, the right part is the left part a bit above. And then you can squeeze it, and then the right part just takes the left part a bit above. So, constructions like that. It will correspond to projection of a hypercube, actually. So, things like that give examples that bring you good constants. But all the things about upper bounds are people a priori assume a certain structure on sets like that and do the calculations for L2 norm, which is doable, and get it, nothing like for L1 norm. But the idea that if it's small, then it has to have a certain structure, it's flying on the air, but there's no way you can quantify it. It's just too, little is known.
If you change the problem a little, work on a torus instead of a square, and define discrepancy with ball
Yes.
instead of rectangles, or ellipsoid.
Yes.
How does the problem change?
There's a whole theory on that. It seems like this one is somewhat the hardest, because you can think about, some surface, and instead of these rectangles, some, I don't know, homothetic copies of something, right? Many times, see what happens here. I don't know if I still have it. If you have this thing, it's a rectangle, but you have to have, all kind of relations between sides. It's not a square. Well, if you're thinking about things which are square or circle, or you're thinking about notions like that with respect to homothetic copies of that, that's a whole different thing. I believe it's in much better shape, because the examples are not something like that, but the examples are, take that whole torus, roughly speaking, divide it in a very small net, like lattice, and take uniform in every small rectangle. So constructions like that, if you average, some of them typically does the job. So at least for known examples. And upper, lower bounds more or less, coincide. But for examples like that, when it's all kind of relations between sides, this doesn't work. Basically, any averaging technique fails. You have to be very specific with the set that you're doing, because this, is very, it fills the set very well. I guess one manifestation of it is that what I was saying, that L infinity norm is obtained on a very small set. So if you change it a little bit, it just fails and goes away. So all these examples with averaging a bit here and there, they just fail. You have to come up with a very specific construction. But again, this is a whole theory developed. I think one of the main persons there is Joseph Beck, and he has a whole like list of results there. They are very different in nature because this one way of exempling is a somewhat averaging argument, but it's an area, and one can find a whole list of results there too. If you allow, what happens with rotated rectangles is like you can rotate your set to a different angle or things like that, and you can get things. But the thing is, like, this problem is where all the problems already are. It just hits the problematic part right away. That's why I wasn't trying to give you somewhat a general picture and general results, but just boiling down to this is where problems are, and this is when you're alone against the problem and can't do much beyond. You allow yourself more freedom, and what happens is that if you want to find, say, a set that is good for them, you just take one of these sets and rotate it to a bad angle with respect to your rotations, something like that. So you have to be bad, because any uniform and good is not good for this. The stranger it is, the better. So it's like you have that, you allow yourself rotations, I guess that's what you are saying, instead of just axis parallel rectangles, and you allow yourself rotations. Your set has to be rotated in a way that your angle does not correspond to the angles that you are allowing yourself to rotate. So there's like a bad correspondence, and you can get some estimates from there. But there, it's upper, lower, are just so far away that you are in even worse situation. You can say some things deriving from there, but you cannot say